All right, hello everyone and welcome back to our last talk before lunch. We're very excited to have Ayan with us. Ayan is a research scientist in the Institute for Experiential AI at Northeastern. He focuses on turning RNA biology using multi-omics data. Maybe you can tell us a little bit about what that means, but he has published very widely in the physical sciences, bouncing between quantum field theory, socioeconomics, heavy quark physics, you name it, he's probably worked on it. And today he'll talk about the alliance between machine learning and physics, whenever you're ready.
Thank you, Alex. And thank you, everyone. Thanks for inviting me here. I think I need the microphone on, which is a challenge for a physicist. Sorry, I'm inappropriately dressed for this conference, but that's primarily because I have a client meeting immediately afterwards. So we are doing it academia a bit differently. So I am at Northeastern. Today I'll try to give you some overview of what we've been doing for machine learning and physics. It's really an alliance of the titans and not a conflict. I'm setting up the neural dynamics lab at Northeastern and work with Storm and also with Brigham and Women's. So if I can get this to move, there you go. That's been my past, making a lot of plots. I still make plots. And right now I'm there as a research scientist. We are mostly funded by NIH, although we are trying to get money from NSF too. And this is most of my past, part of my present, but what I really try to do now is applications of machine learning in RNA biology, and the reason I'm doing it is to develop therapeutics to slow down or reverse diseases, terminal diseases, cancers, et cetera, mostly so that we can live long enough to see results from the future colliders. So I took it the other way around. I mean, you guys are building the colliders, getting the results. I'm making sure we live long enough to be able to see those exciting times. But jokes apart, I've also participated in some of the initial work that went into designing FCC and the other colliders, but not going to talk about it today. So first of all, there's no artificial intelligence. And this is going to be a light talk the way I start. So, and the reason the reason is because we have examples of natural intelligence and we've relied on them in the past. And there's some examples of sporadic intelligence, which also kind of works most of the time. And AI really is in movies and books right now. So we don't talk much about AI in the Institute. What we do talk about is glorified regression, which is also machine learning. Now we can go into an argument where machine learning stops and where artificial intelligence starts and all of these things, but let's put it this way. Today I'll talk about machine learning. So, or glorified regression. So this is a group of humans trying to make machines learn, and they are a fun group of people. As you see, we are standing outside the Bukowski bar. Those from outside town, if you want a dive bar, that's probably the only dive bar you find in Boston. Unless there are dive bars that you know of, and please let me know. So now, does physics really need machine learning? That's the question. And since machine learning is so trendy, the warning is when you have only a hammer, everything looks like a nail. And that's one thing to learn. Because, and I try to emphasize that because we still use traditional methods to get to answers that really work. I mean, not the answers work, but the methods work. The answers sometimes work. And machine learning, I personally like to bring in machine learning only when it's like really necessary, because it's really a cannon and you don't use a cannon to kill a mosquito. So let's look at the landscape now. This I've shamelessly stolen from Tim Tate, of course, with his permission. And we have a whole host of theories, and my apologies for being negative, but really I am pretty excited about all the theories because at heart I'm still maybe a theorist. But none of the theories we have proposed have shown signatures in experimental probes. So we haven't really found BSM in the easy way, which means there is no real naturalness or hierarchy problem per se in the way that we had envisaged earlier. And if nature really wants a mass gap, it gets a mass gap. We have nothing to do about it. And if there exists a mass gap and data is sparse and very noisy and everything, we do need to gather a lot of it. And when you have a lot of data, a lot of higher dimensional data, that's where machine learning kind of shines or starts to shine. So there's, and we've heard in the past, in the two talks today morning, how we can go different paths and kind of do a model-based or a model-agnostic kind of an approach. But machine learning is a space where both can be implemented. Now, in a roadmap for the future, we will have a lot more data and a lot better statistics than what HLLHC will give us. And we really need machine learning to analyze all of that data, because machine learning, the question really is it the new math that we need to find new physics? And I do believe that it is. It's not a new math, it's been around for too long, but its applicability has exponentially increased. And hence I feel that it's a good spot to start. Now, in the next few slides, I'll try to explain what ice is to the Eskimos, so please bear with me. But I'll just go over what really machine learning is and can it be used to understand the laws of nature. So some historical perspective, machine learning really started as a rule book. And people, after they figured out how computers work, they really wanted to encode everything into a rule book so that if you ask the rule book something, it will give you back an answer. Because at that point, intelligence or human intelligence was really confused with human knowledge. And knowledge and intelligence are, to me, different things. One is the derivative of the other. And I'll let you figure out which one is the derivative of the other. So the rule book of everything really didn't work, because at some point we realized that knowledge is too vast and really out of sample is a problem. So that kind of didn't work, and we realized that Newton was right 300 years or more back, and it's still valid that we're really exploring a very small, tiny fraction of what the universe really has to hold. So the solution really is you observe and you try to extract information or patterns from the observations that you make, which takes you directly into the data-driven or the statistical regime. So you have what you really need is statistical learning. So Turing set forth some requirements for an intelligent machine. And one was natural language processing, because that's the mode of communication, and information has no sense without communication. So there's natural language processing, there's knowledge representation to store information, and there's automated reasoning, which would use that stored reason to come up with certain series of logical statements. And then, of course, there's machine learning is to adapt to new circumstances and extrapolate on patterns that have already been learned. So beyond Turing, of course, you can define computer vision to perceive objects and robotics to manipulate objects. And this essentially puts together a framework with which you can learn and manipulate the environment around you. And statistical learning has so far outperformed rule-based algorithms by far. And how useful is it to physics? We must remember the physics goal really is to extract and process underlying patterns in data to discover the laws of nature. So natural language processing, it's not being used so much because sequence analysis hasn't found a lot of application. Knowledge representation is essentially lower dimensional embedding, which is fine. And automated reasoning, now, I don't think we've come anywhere close. And machine learning has become the backbone of experimental analysis. A lot of it is being used to phenomenology and theory too. Computer vision has found widespread applications, and robotics, no. Yes, it's still here sitting in person doing our jobs. So now, of course, historically, you can do a classification, or you can do unsupervised learning, which is clustering. And there's been plenty of algorithms that have done that. Decision trees have ended up being pretty useful. SVM, there was a time for SVMs, but SVMs gradually faded in the large data regime. And decision trees kind of tend to rule when there's pretty much tabular data, there isn't any non-Euclidean data or images or etc. And you'll see the absence of diffusions and transformer models here because this is an old picture. But you do see the exponential growth of application of deep learning, and I don't have to explain that to this community why and how, but it started in 2012, and what really happened in 2012 was A, Higgs was discovered, and B, deep learning emerged as a leading statistical learning method for several reasons, and C, I completed my PhD. And one of them is causally connected to this exponential growth. So now, so why did it take so long? This is, I think Hinton said this, but I'm not sure, so I just put in some giants of ML, but I should know for certain this was said that our labeled data sets were 1,000 times too small, our computers were 1,000,000 times too slow, we initialized the weights in a stupid way, and we used the wrong type of nonlinearities. And this pretty much sums up why statistical learning wasn't working as well as it should have. So it's really a lot of training data, parallel computation, scalable and smart algorithm, and that takes you to machine learning. So if you can't do all of, this actually takes you to neural networks. If you can't do all of them, there are other methods which are sometimes included in machine learning. We must remember linear regression is oftentimes called machine learning, and we can do that with 2 data points. Can we do physics with machine learning? Yes, there's lots and lots of data. We have fast computers now. We know how to initialize the weights and etc. Moreover, we have some estimate of the models that we are trying to probe. We know what symmetries we are trying to look at. We know what symmetries are broken, etc., etc. All of these are wonderful things to know. And as far as the nonlinearities go, those have been solved for a bit, but really what we are trying to do is figure out coefficients of nested functions. So that shouldn't be too complicated from what we were doing before, which was coefficients of motivated models. Oops, wrong direction. So yeah, I'll skip this slide. We know what we can do with machine learning. So there's a whole bunch of stuff we can do. So 2 examples of machine learning that I'll go through, and these are work that I've done, so they're heavily biased towards what I like to do. But the first one is high precision regressors. Now, this work I've been doing with Fadi and with some other people at Northeastern. And the goal of this is really to make sure that those feature colliders we are building, we have the capability of doing enough simulations for them for both the signal and the background and everything. And at this point, of course, next to leading order is important, N3 LOs coming in. There's higher order calculations will become important. The higher order calculations, we all know, are really slow. And that makes Monte Carlo generators really slow. And we can't really afford that because we do it over and over again. And we have to do it a lot of times. And there's another aspect to this, which I will discuss later in the talk, is really it's a question of energy usage too. Because we leave a carbon footprint. I know in the grander scheme of things, it's not a whole lot, but it's still something that we can cut down on our way to contributing to any actions against climate change. And that I will mention in the end, but okay, let's go on with this now. Again, this is something which is a kind of universal in all sciences that use Monte Carlo generators or Monte Carlo simulations. The real problem is that somewhere out there, you're evaluating a function. And when you evaluate a function, there can be stuff in there that takes a long time to evaluate. And if you do this millions of times, this just adds up and multiplies and etc. And then you end up with a few seconds per iteration. You have to do millions of them. You need giant clusters for those and etc. But one has to be careful with Monte Carlo simulations because oftentimes they're the kernel of an integral. And if you have large errors in there, then you just blow up the integral in ways that you don't want it to blow up. You get large errors. And as we well know, quantification of errors in machine learning is a problem. And you don't want to be predicting or regressing in parts of phase space which you're not kind of certain about, which means if you use machine learning to approximate any of these functions, then you have to have pretty high precision at all parts of the phase space. Fortunately, we more or less know what part of the phase space we are looking at. That's pretty well defined. So something which is completely out of sample is unthinkable, kind of. And if it arises, you can always do this, extend the simulation and build another model, but really high precision is of paramount essence. The reason I'm emphasizing on this is because it's not so easy going down to this even with even in smaller dimensional space, and by small I mean 8 dimension, 10 dimensions. Now, we don't really have to probe really high dimensional space, let's say in particle physics simulation. So I wouldn't be a ton worried, but I'd still be worried, and I'll tell you why. So if you break down a matrix element, there are parts of the matrix element which, especially the higher orders, which will be really, really slow. And why do we know it's the, I mean, the easy argument is we know how to do the integral. That's not a problem. That's been sped up sufficiently so that we don't have to worry about that. What really matters is the kernel of the function and the kernel of the integral. And the kernel of the integral has parts which are really slow. So instead of trying to generate the entire integral, why don't we just generate the part that is slow and let the Monte Carlo integrators do what they are really good at. So what we did was we kind of pulled out the part that was really slow, and then we trained boosted decision trees, deep neural networks, and we came up with this funky architecture which has a skip connection, because why? Skip connections always work. And there's half a library full of literature telling you why skip connections work and showing that skip connections work. So we took a deep neural network, plugged in a skip connection, and we trained it again. Of course, we got better errors with the SKDNN. What is important is, again, remember, we are not aiming for a single parameter telling us that we've got 99.99% accuracy. We are aiming for accuracy over the entire phase space. And what do we get? We look at distributions of errors. This delta is really a delta. It's the difference between, it's a percentage difference between the real value and the predicted value. And of course, in 2 dimensions, it doesn't matter what architecture you use, you get pretty good precision. I mean, boosted decision trees really outshine there. But as you go higher in dimensions, the boosted decision trees do start suffering. And at that point, you see architectures like SKDNNs, which even with lower degrees of complexity can outperform the other architectures. And we were pretty happy to see that, because that kind of solved the problem of slow Monte Carlo simulators. But this is the key plot, I'd say. And the key plot is that in parts, the skip connections really do much. What you're looking out for is reds and oranges. You see there are much fewer reds and oranges in the entire phase space compared to the other architectures. So really, skip connections do wonderful in kind of flattening out the error curves. The second thing I want to talk about is interpretable machine learning. And this is in learning Higgs signals. This is work again done in the recent past. And the idea really is to pull out the BB bar production from Higgs. And while it's a very large signal sitting out there, what really is a problem is the background, because you have a continuum background coming of BB bars. And if you look at the final state BB bar gamma gamma, then you have a very huge background compared to the signal. It's a signal to background ratio of 1 to 250. And that becomes a challenge because traditional cut-based analyses don't work. So what do? We do what experimentalists have done for quite a while now, use boosted decision trees instead of a cut-based analysis. But the key here is not to repeat what has already been done, because everyone knows boosted decision trees is going to work better than cut-based analysis. The key here is that if you run boosted decision trees with the phase space variables, then you get a finite set. But those phase space variables aren't really the 4 vectors. If we run it in terms of the momenta 4 vectors, then it's not really very interpretable in the sense that we understand what particles doing what. But if you move into these kinematic variables, you understand, because we've been tuned to understand all of these things, and these have some meaning. But if you use this, this is not a closed set. This can be, you can basically keep on listing as many kinematic variables as you want. Some will have, some are correlated with each other, some are not, some are marginally correlated with each other. So you really have to pick and choose which are the most important ones if you want to do a quick analysis. And if you see how the distributions lie in each of these spaces, these are, some tell you that the signal is clearly separable, some tell you not. And so it's difficult to figure out what variables will actually help. Now, if you look at correlations too, it's a devil understanding which ones will disentangle and all. And then, of course, these are just linear correlations. You have higher order correlations, which you cannot plot. And so cut-based analysis really don't work, whereas machine learning algorithms will more or less wrap themselves around the distribution and extract the other distribution. So it's a no-brainer to kind of use them. What we use to make things interpretable is Shapley values, and pretty sure many of you are familiar with what it is, but it's really a card game. And in a card game, you can either play against another player, which is non-cooperative game theory. Shapley values come from the cooperative game theory part, where you have a team playing. And let's say there's $19 at stake. So the team playing together would win $19. Now you can, if you know how, if you kind of know how each player plays or kind of estimate that, you can say, okay, if A plays, A makes 7, if B plays, B makes 4, C makes 6, etc., etc. If B and A play, they make 7, and you get an estimate of how much they make, right? And then what you do is you play all combinations of the game. So A goes first, then C, then B, and you pull out these numbers. A makes 7, and A and C together makes 15, so C makes 15, and B makes the other 4. And you play all of these games, you marginalize it, and if you marginalize it, you get a value of player A, player B, and player C. And the intrinsic value that player A, B, or C brings in is actually called fair attribution in game theory and maybe in legal terms too. So here you see that C has the highest value. So if you were to not play the game and just take $19 and distribute it fairly amongst the players according to their abilities, you would give C $8.1, whereas you would give others. Sorry, picture is gender biased. I could not find a picture where men and women were playing cards together. Well, I'm pretty sure that wouldn't be a problem. But okay. Some properties of Shapley values, the reason why we like them is that if there's a dummy player, a player who doesn't contribute anything to the subset of players, the Shapley value is 0. And this is very good because oftentimes we find authors in papers who have contributed nothing, but we give them non-finite Shapley values. Okay, sorry, bad category jokes. So there's also efficiency where the attribution must add up to the total gain. This is absolutely necessary in a fair attribution scheme. There's symmetry, which is that symmetric players, if K comes after I or I comes after K, the attribution should be the same. And this is not only a good property of Shapley values, but it's also a limitation. So if you want to do a symmetric Shapley values, the first thing you throw out is the symmetry assumption, which does give you some way of looking into causality, but we won't go into causality today. We know physics is causal. So, and then there's linearity, where linearity is always good to have, because then you can add up different games and you can say, okay, this is how things are working. So with that, you have the Shapley additive explainers, which is a fantastic way of analyzing boosted decision trees. And what it really probes is cooperation in physics. As you see, correlations can be pretty similar between signal and background, but then if you look at it using Shapley values, these actually get disentangled. So what you're doing is converting a black box into an interpretable machine learning framework. And this is a little thing I want to show, that if you really want to be interpretable, you'd have to go back to linear regression or decision trees. And most of the models we use are not interpretable or explainable. There's a difference between interpretable and explainable. I won't go into the nitty-gritties, but explainable means post hoc explanation. Interpretable means the entire framework being interpretable. We do call it interpretable machine learning because we can open up the decision trees and we can actually see what's going on in there, and you'd see the Higgs peak in there. I can guarantee you that. So this is the framework we follow. We do a bunch of simulations, which some the signal and background, we push them into boost edition tree for signal classification, and then we calculate Shapley values, and voila, Shapley values tell you which variables are the most important, which kinematic variables are the most important. You'll see some ones which are very obvious in this case, which is n gamma gamma. Of course, that will be pretty obvious because that's the Higgs peak. But then you also see some which are not so obvious, and you'd be a bit surprised why they actually exist. So I won't go into the details of the analysis itself, but you can do it the traditional way too. You can extract parameters and etc. From your machine learning output. But what to me is really striking is that you can actually see which kinematic variables get boosted by which channel. And then you can make fancier plots to understand why this actually works, and that's because Shapley value actually deforms the initial kinematic distributions through the boost edition tree. Why? Because the boost edition tree is used as the characteristic function of the Shapley value calculation, and then the Shapley value really tells you that even kinematic variables which look similar in their kinematic distributions are really different in the Shapley value space, and that's why they get separated. Okay. So this is my summary to the physics part of it, and it's sorry, we still have to write our papers, but machine learning has made a dent. We'll continue making bigger dents, and we are just really at the beginning of where we can get to with machine learning. And everyone knows this living review, but if you don't, please visit it. It has all the papers in there. Now, I just want to put in a word about sustainable science, basically a path to reducing environmental footprint. It's a bunch of paths working together. Rafi's here too. Rafi works on it more than full time. So while doing fantastic research in physics. So this is an attempt for us to see if we can reduce our carbon footprint, essentially, or make sure that we are not criticized overtly for the research that we do, because we know our research leaves impact. But if our research is also leaving a climate impact, it's a problem in itself, but it's also a problem because it's going to be severely affected by cuts on sciences that leave excessive carbon footprint. And I don't need to tell anyone here, because we are all from a computational community. We do use a ton of computers, and we burn a lot of energy. So this sustainable decap reflection document, it's a good place to start if you want to look this up. And we address many issues, some which can be argued are not specifically in the line of the profession, but at the end of the day, it's humans doing work. So many things that we do, even personal choices that we make, end up being part of what we are and how we live. Like travel, certainly there's a personal part and a professional part, but then sometimes they get entangled, so we have to look into everything, give everything a hard stare. Now, the IPCC, which basically, let's say that's kind of the UN on climate change, and they have in no uncertain terms said that the problem is now. In fact, the problem was yesterday, and we will have unreasonable increase in temperature in the next few decades. And if it matters to anyone, tropical countries, and it matters to me because I'm from India, and tropical countries will have over 6 months of excessive heat. And when they say excessive heat in tropical countries, that's really bad, because anyways, it's excessively hot in tropical countries. So it's going to get really bad, and that's not even questionable. That's going to happen. The question is, can we stop it from getting worse than this? That's the real challenge. So what we try to do is we try to address different aspects of our research lives. One is computing, the other is energy, food, mobility, research infrastructure and technology, and resources and waste. This is my pet topic, but then I will talk about computing today. We try to break down suggestions into individual suggestions, groups and institutions. These are not instructions, these are suggestions. So We try to follow the UN Sustainable Development Goals, the SDGs, which outline how development should progress if it has to leave least impact to climate, maximum impact to social justice. There's always a component of social justice in all of this, primarily because it can be shown that the highest income bracket is the largest contributor to climate change. This it can be irrefutably shown. I don't have that plot in here, but I'll just state that. So we break up the different parts into its impact on SDGs, their impact on SDGs. And in computing costs, we know that there's a high energy consumption part, and this needs to get changed. Oh, exabytes of that. Anyway, so this is a part where machine learning can contribute. Because instead of doing things explicitly, if we approximate things, of course, consumption goes down. And if approximation takes more energy than exact calculations, let's do the exact calculations. So, and there are certain cases where computation is not even possible. We keep trying, but we know that that's not possible. So maybe keep an eye out for that. And then, of course, there's individual impact to climate change, and I will finish soon. So we have some individual recommendations. I think I forget which institution has implemented this, or it was a suggestion to implement it. Every job should come back with its carbon footprint as an output, so that we know what we are doing. And that's not a complicated calculation, but we don't really do it in our head. We know that 10 jobs cost more than one job, but we don't really know how many trees we are burning with 10 jobs. So that's probably something that can be implemented at the personal level to keep an estimate of what we are doing, follow some best practices. In physics, we focus on physics, but there are parts of scientific community which actually focus on sustainability and climate. Maybe take a leaf out of their book and see what they say about what we have to do. There's, of course, group actions as collectives, as collaborations. We can take certain actions to minimize our output, and this can also be things like determining where we put our servers, where we put our data centers, etc., etc. Underwater is a nice place for cooling, and several companies have explored this. So there's things that we can learn from them, and of course, at the institutional level, this does not mean don't give a computer to everyone, because of course we need computers, but more efficient computers moving to, let's say, ARM versus x86-64, which has a lot less joule heating, is probably one way to go, and all of these things. So these should be taken into consideration. Lifecycle analysis should be done, and all of these things. So with that, I will just say that we are trying to organize a workshop on sustainability and computing. We don't know where it will be. We are looking for organizers, etc. If you want to participate, if you want to contribute to any of this, you can get in touch with me, or you can get in touch with Daki, or just Google us. You'll find who to get in touch with. Send us an email. We'd like a wider participation, especially we'd like a wider participation in the United States, so that we can get this going. So that's my final statement. There's an open position in biology if anyone of you want to move to biology. But we do need some knowledge in biology, so read those books that you read in high school and come to me, and I'll probably consider it for you. But this is serious work. This is in plastic degradation, so you'd actually be contributing to breaking down that big patch in the Pacific. And I'm not joking. And thank you very much.
Invoking the last talk of the morning session. Other questions for Ayan?
Yes.
So as much as I might tend to actually about the last part of the talk, which is fascinating. In terms of interpretable machine learning, there's the question of course, what I learned in terms of understanding how choices are made, but then there's a question of actions that I would take. So given your table of Shapley values, like what's the intervention? You said, okay, we can trust our machine learning. There's one question about like how to say that yes, I'll trust it, and also in the case that it doesn't correspond to what I anticipated it was going to do, what the next step is. So can you talk about that? What does it look like when interpretability goes bad? and that you say you didn't understand what was going on, or a decision was made in an inappropriate way. What do you, first, how do you see that, and then what are you supposed to do in terms of an intervention?
Okay, so at Northeastern, we keep talking about human in the loop. I'm a bit, I don't know, I'm not, the way I would like to put it is, when you get an inference from, let's say, Shapley values, there's two things you can do. First, you can ask yourself, is the Shapley value correct, right? And if your model is reasonably predictive, and Shapley value really, if you go through the framework, it's nothing but probing higher order correlations. So if your system has higher order correlations and the model kind of models it well, chances are the interpretations are going to be right. However, if you have a system where the signal is not large at all, and here the signal is pretty large, signal can be much smaller. If you, let's say, get a R square of 0.2, 0.3 from your model in a regression task, interpretation is not going to work. Because the reason why the model cannot model that system is because there isn't large signal in the system. And this is something that people miss quite often. They use interpretability in using models as characteristic functions, which are not really modeling the space really well. And that is where the human judgment comes in. At that point, you can say, I've built a model, I've done my Shapley values, I've done my due diligence, let's go with the Shapley values, or no, I think the model's not good enough, let's try again. So that's one thing you can do. The other things, as far as interventions go, is that if you do have confidence in your Shapley value, you think that your model is doing reasonably well, and at that point, the question really is, do you use the model blindly, or do you also take into account your Shapley values? One use case would be, if you don't know what kinematic variables are important for the system, which we know pretty much for some systems, but we might not know for some other systems, then you just throw in all kinematic variables, hoping that something will work. You get a reasonable model, and then you say, okay, now I understand that these kinematic variables don't matter at all. What matters is maybe the first three or the first four, and why don't I focus on that? And suppose I have to build a detector based on that. What kind of a detector would I build? Or where would I put in my most efforts to probe the system? In particle physics, of course, we have general purpose detectors. You don't really base it on one analysis, but this can be a use case in several other branches of science. And so really, what you do with the Shapley value depends on how well you've managed to model the system. And once you have confidence in the modeling, you use the Shapley values to reduce dimensionality maybe. That's one use case. The other, of course, is like, there have been cases in which we looked at the variables and we are like, what is this doing here? Why is it important? I thought this variable had absolutely no power to separate signal and background because the distributions are exactly the same. But then you understand that this variable has very large correlation with other important variables. And by having large correlations with these variables, they're actually skewing the distribution, and hence they become important as a team player, but not by themselves. And this is something you don't get to understand from 1D distributions or 2D distributions alone. So there is some space to play around.
Other questions? I'm just gonna double down on the Shapley value question. So when you showed that slide with the Shapley values, it's sort of like this really simple bar chart of like you ranked all the features by the Shapley values, highest to lowest. But as you mentioned, like these sort of things are calculated by looking at like these very high order correlations, and so like these features aren't existing in a vacuum by themselves. They're sort of like interplaying with the other features when you're looking at the grand scheme of the classifier. So, I mean, you mentioned sort of using it as feature importance, which is sort of a murky phrase, but like, yeah, like, for example, you can throw out, like, if something has a low Shapley value, you'd probably be pretty sure that it's not important, like by itself or interplaying with other things. But are there sort of other conclusions that you can draw besides just low Shapley value, like low importance, like sort of what are the other uses besides reducing dimensionality? So
two parts to the answer. The first part is if I was doing law, I'd be really concerned about the difference between HT and M gamma. If I'm not doing law, then if I'm doing physics, I wouldn't be so much worried because, I mean, these bars are pretty different, but let's assume they weren't, they were pretty close to each other. Then I'd start worrying if I were not doing physics. In physics, we have this leeway of saying, okay, we don't need the top variable. We don't need the top. We are okay with saying like top 5 seems to be giving me the sufficient variance, and which is something that you do in a PCA too, but in a PCA, you just go multi-via doing the PCA. The second thing is, in feature attribution, correlations is a problem in many fields. Again, in law, it's a problem because if my contribution feeds into your contribution and hence you can make more contribution, then it's a problem. But in physics, again, if two variables are really correlated and together they are giving you a better result, fantastic. So, the feature attribution as spoken in terms of social variables and spoken in terms of physics variables do have a difference. And when people say, oh, it's a highly correlated system, you shouldn't be calculating Shapley values. I was like, yes, for a social system, yes, you shouldn't be. But for a physics system, please go ahead, because then we know the bunch of variables. The second part of the answer actually is that you can do more than univariate Shapley values. There's a structure called bivariate Shapley values, which essentially, in very simple terms, is the off-diagonal. And in bivariate Shapley values, you can actually examine which variables make which others redundant, or which variables make each other mutually redundant, or things like that. And you can ask those questions. The reason I don't use that or don't use that framework extensively is because the interpretations are still not well understood. It's literally like they came out a couple of years back. And we're still working on those to kind of understand what they say. And they do need better models, because if the model doesn't have a very high high control over the signal, then bivariate Shapley values would be shakier than univariate Shapley values, the biggest obvious reasons.
Thanks.
Yeah.
Final question? Yeah.
Yeah, thanks a lot also for the second part of your talk on sustainability and environmental issues. I have one concrete question, like whether you have any suggestions or ideas, like on how to break what's called the Jones paradox. Have you heard about that?
Tell me.
So just historically, like as for example, computation, I mean, this is true for many other things, but as computation, for example, gets more efficient, it turned out like we just computed more, like the demand increased. And this is universally true for many other things like mobility and these kind of things. I was wondering whether you have any suggestion on how to break this, or like, I mean, I guess as computation, for example, becomes more efficient, like many scientists would just want to compute more, right, and do more science and do more.
So yes, this is exactly what consumption is. The cheaper something gets, the more of it you purchase. And so the way I put it is that we love doing supercharged science. We want to get to the answer as quickly as possible. But really, as scientists, we should sit back and think, if I do it in 10 days instead of 5, maybe I'll miss that paper by the end of the year, but does it really matter? I have a very good metric attached to it for my personal life, and I'll share it with you. I ask myself, is anyone going to die? If no one's dying, I can afford to slow it down. If someone's dying, of course, and of course the perception of dying is another issue altogether. So grad students might die if you don't produce results fast enough. But I'd set personal goals for that and say that this can slow down a bit and this can't, and kind of build the priority. And that's the only way to slow down consumption. You ask yourself, do you really need to buy the bottle of Coke? So that's the only way. I mean, there is no way of forcing people to do it, because then science gets skewed. There's no legislative way to do it, because scientists don't work on legislations, or hopefully we won't have to. So really, it's also a matter of making sure that those legislations don't come into place to limit our science just because we didn't do enough to limit ourselves. So at this point, that's the question we really need to ask ourselves. Otherwise, of course, if you want to send more jobs because the computers are faster, that's a question of choice, really. So, which is why our professional lives and personal lives aren't separate. They're entangled.
Okay, thank you.
Thank you.
All right, we're out of time, so let's thank Ayan again.
Thank you.